Hello and welcome to a new episode on Hyperbolic Orbits podcast. And today we are going to launch a new kind of format on this podcast where space professionals working on some really interesting projects are going to discuss and tell us about their fields of expertise and what we can learn from it. We have with us Jared Long Fox, who is a planetary exploration research scientist at the University of Central Florida, where he leads projects advancing surface and subsurface exploration technologies for the Moon, Mars, and other planetary bodies. He is a visiting researcher at the NASA Kennedy Space Center Swamp Works and a visiting technologist at the NASA Jet Propulsion Laboratory. Jared's work seeks to develop next-generation robotic planetary exploration and infrastructure development systems and scientific instruments. Jared also serves in leadership roles with the American Society of Civil Engineers Regolith Operations, Mobility and Robotics Technical Committee, and the American Institute of Aeronautics and Astronautics Space Resources Technical Committee, where he leads education, outreach, and open collaboration across the space resources community. Thanks a lot, Jared, for joining us here today.
Of course, Sumana, thank you for having me on. I'm a fan of the podcast and really excited to be here and share about some of my work. So I do have some slides to share for everyone, and I'll share in a minute. But first, I wanted to give a little bit of background. And well, actually, I have a slide on this, so I'll start sharing now. Yeah, again, thank you, Sumana, for the introduction. As she said, I'm Jared. I work at UCF as a planetary exploration research scientist. The fundamentals of my research focus on planetary regolith characterization to enable safe and sustainable space exploration and resource utilization. Now, that's a lot of technical jargon. We're going to dive a bit into what that means here. But first, like I said, a little bit about me. I have a bachelor's degree in geology with minors in mathematics and geospatial technology from the South Dakota School of Mines and Technology. I also got my master's degree in geology with an emphasis in geophysics, where I did a lot of studies of volcano deformation, kind of trying to get at volcano eruption prediction. In that time, I actually also worked with my advisor and his lab group to develop some, as you see on the top right of this screen, some volcano exploration rovers to roll around where humans really can't and take hazardous gas measurements, GPS measurements, and so on, things relevant to characterizing volcanoes and figuring out, are they getting ready to erupt? That exploration, that project really kindled my fascination with exploration and robotic exploration in particular. Like I said, I was a geology major who happened to get interested in programming and robotics. I took a lot of my own time and worked with some really good people to learn this stuff, but the exploration is what really always had my heart, and I didn't know that looking back, but looking back, it's obvious. So like I said, my research interests are in scientific exploration and enabling that through resource utilization, specifically in space. To do this, I research things like planetary surface physical properties. I do high performance computational modeling. I work with lots of robotics and electronics, volcanoes and earthquakes here on Earth, and general exploration and sensing, both here on Earth and in planetary environments. And today, I'll be largely talking about the planetary stuff. So moving on, some of the key research questions that I'm going to dive into today, and I'll be giving answers to each of these, and we'll be walking through them together. But the first is, well, what testing materials do we need for scientific research and development of hardware for space exploration and settlement? How can we characterize the in situ physical properties of subsurface planetary regolith? And finally, how do the physical properties of planetary regolith affect rover trafficability and vice versa? The first one really focuses on the fact that we don't really have appropriate analogs here on Earth with which to simulate the planetary surface. For example, when we send a rover to the moon or Mars or something, we can't just we can't test it here on Earth using beach sand. The ground is fundamentally different on the moon and Mars, and Mars isn't an airless body, but in general on very thin atmosphere or airless bodies, because the planet doesn't have atmosphere to really protect it from all these little meteorites and micrometeorites and that come and impact the surface over billions of years of geologic time. It kind of grinds up the surface through impacts. Even the little ones can break apart little grains on the surface, and eventually over time you get this extremely fine dust that you see in all the videos of the Apollo astronauts from the 60s and 70s, and in pictures on Mars from dust devils and stuff like that. So because the material on these bodies is so fundamentally different than what we're used to dealing with here in our daily lives on Earth, we need to actually develop these appropriate analogs, these regolith simulants. That dusty material that I mentioned on planetary bodies, it's called regolith. Rego meaning to cover, and lith meaning rock in Latin, actually. And it's oftentimes referred to as lunar or Martian soil, and that's technically not accurate. I won't dive into it, but it's got to do with organic content and no defined horizons. So anyway, a soil is like a regolith, but a regolith is not necessarily a soil. One of my little nitpicks that that I have on the terminology, something I probably shouldn't spend as much time worrying about as I do, but hey. So that dirt, the regolith on the moon and Mars, like I said, it's nothing like we have here on Earth. There's all sorts of different processes including space weathering, like radiation environment, electromagnetic environment, different mineralogy, and no atmosphere, or a different composition of atmosphere. A lot of times people try to use things like beach sand, cocoa shells, or whatever to test rovers, landers, instruments, astronaut suits, and so on. And it's really just not appropriate. It introduces a lot of risk by assuming that material is going to behave and perform the same as the regolith on the moon. So we need these high-fidelity simulants, these regolith simulants that are really good at replicating the chemistry and the physical properties, like how strong is it, could a rover drive in this, that kind of thing. And our lab group at UCF personally goes about making simulants through mineralogy and particle size distributions. Mineralogy of a part of anything defines the shape and density of that material. The moon, Mars, and asteroids are, like I keep saying, really different than anything that we deal with here on Earth. And each mineral within a rock or a regolith, which rocks and regolith are made up of a bunch of different minerals, because the regolith is just crushed up, impact, ground up rock. And each of these minerals has a specific atomic arrangement, literally down to the quantum level, that gives it its specific properties, whether that's its preferred shape or planes it likes to break upon, called like cleavage planes, and how it breaks apart when it's hit by a small impactor and stuff like that. And all of this on Earth is usually driven by wind and water processes. But on bodies without an atmosphere, like the moon, for example, the shape is driven by impacts. Like I keep saying, you see the theme here. And until relatively recently, most simulants did not actually consider the importance of mineralogical accuracy. A lot of them were these geotechnical simulants that were supposedly good for testing things like rover mobility or developing a lunar roadway so your rover can drive around easier, or all sorts of things. But these geotechnical or mechanical simulants are just rock here on Earth crushed to certain particle sizes without much of a care for the mineralogy, which, like I said, that really mineralogy impacts everything: frictional relationships, particle shapes and sizes, and hence how they flow around each other when you're excavating or something. And testing with these inaccurate materials leads to inaccurate results. So I should do my due diligence and go back a bit and say, well, who cares? Why do we want to excavate or drive on the moon or Mars? And it's partially for scientific exploration. What we learn out in space really benefits daily life here on Earth. Things like Velcro, or hook and loop tape, as some call it, or a cell phone, are really thanks to space exploration activities around the world. These technologies were developed and transferred directly into our daily lives in the form of phones and much, much more. It's also to help us better understand the universe and the solar system around us, where Earth came from, and these sorts of fundamental questions. Why would we want to excavate and use resources on these surfaces? Well, because we don't want to have to launch a ton of stuff from Earth. Launch costs are extremely high, and the more we can figure out how to use on the moon, use their in situ or in place resources that are there, the cheaper and more sustainable our exploration will be. It'll enable us to not only do it for cheaper, but for longer, and to extend our efforts further out into the solar system. So we do want to be able to use these in situ resources through in situ resource utilization, ISRU, whether that's generate oxygen or from the regolith, or generating metals from the regolith, which we can use to make propellant or make parts for buildings, or repair a rover, that kind of stuff. So it's all kind of coupled, and my goal is to contribute to all of that kind of at once. And like I said, to do that, we need these high fidelity simulants. So literally starting from the ground up. But we make these simulants. I'm with the UCF Exolith Lab, where we make these simulants available for bulk, and we can distribute them to various entities, whether it's NASA, the European Space Agency, ESA, JAXA, private corporations, or academic institutions for use as well. But we have these great materials that we can test with that are really realistic, but the test results that we get don't really mean anything unless we actually quantify, do testing to understand the properties of these simulants, such as their shear strength, how they compress when you step or drive on them, their density, which affects things like suitability for developing a lunar base or mapping out safe traverses for rovers. We also need to understand things like how they store and retain and transfer heat, as well as their electrical properties. These materials are these really, really fine grains, below millionths of a meter, submicron particles on the nanoscale, like billionths of a meter scale sometimes. They're at the size where they have really interesting electrostatic properties, like we wouldn't see with beach sand. Because the particles are so small, a lot of the interactions that they have with each other and their environment, at least on the moon, are from van der Waals forces, these atomic scale forces, electrostatic forces that interact between these grains. And that, combined with the extremely wide particle size distribution from like nanoscale up to small cobbles, how these mechanically flow, how they behave during excavation or rover driving, is fundamentally different than anything you've seen on Earth. And you don't really understand that until you actually get your hands on some of this material. But anyway, so why study the properties of regolith and regolith simulants? Well, like I said, it allows us to do a lot better, a lot safer, a lot less risky exploration hardware design. For infrastructure development, such as landing pads, because when we land, we don't Eventually, on the moon, we'd like to have a landing pad so we're not just kicking up a ton of dust everywhere. On Earth, we have launch and landing pads. We need the same thing on the other side, at the moon, Mars, wherever, if you're going to be landing there frequently. For infrastructure development, if the goal is to build a lunar base or to develop some sort of science outpost of some sort, which that's the goal of many entities worldwide, we need to be able to do roadways, building foundations, just like we do here on Earth, but a lot harder because it's on the moon. And similarly, like I've said, we need to actually be able to use the local resources there to minimize our cost to actually get there and do it, to maximize our science returns and how much time we can spend exploring rather than just waiting around and making resources. As well as to advance technologies here on Earth. Things like the ways we're looking at extracting metal and oxygen from the lunar regolith are directly transferable to the industry here on Earth in terrestrial mining. So a lot of the robotics technologies for mining on the moon are going to really help what we do here on Earth, ultimately lowering our dependence on some of these resources for both Earth and space use. So there's really a ton of benefit that can come from this. But I will say that the current state of planetary geomechanics, the way these regoliths behave in terms of how they flow, are excavated, and what have you, and our initial space exploration efforts did not strive to characterize these physical properties. There was some sample return during the Apollo program that NASA did in the 60s and 70s, but these analyses are based on very few samples and really small quantities. We need larger amounts to test, and we need to run more tests. But because of how scientifically valuable, and value is not the right word, how scientifically important these samples are, we can't just run a bunch of tests on them that may be destructive, break some of the grains or what have you. We want them as intact as possible because, well, we have so few. So there have been some efforts to characterize things like safe rover traverse areas with satellite imagery. And that's great, but there's really no replacement for on-the-ground measurements. Now, there is, because of all of these goals that NASA and the Chinese Space Agency have in actual, and many, many, many others around the world have in establishing outposts and having a more permanent, sustained presence on the moon and Mars and elsewhere, there's increased interest in this geomechanical science and in engineering modern technologies to assist with this space exploration. But the problem is, in this field, people often don't know what they need to know or even where to start looking. It's a really complex problem, and often when you're facing a complex problem, the first and often hardest thing you have to do is, well, where do I start? Where do I even start? And that's a big hurdle to overcome. And we're starting to get there. We're starting to know what we don't know and figure out how to learn it in this field. So with that, some of the challenges are the lack of data. We need both data on the moon and in the laboratory, but there have been no missions to actually go characterize some of these properties on an extraterrestrial body. There are mission concepts, instruments being developed, and some even manifested for lunar flight. So this is changing, but to date, none have actually launched yet. Some studies have tried using opportunistic measurements, like using a rover wheel and making it slip to try to figure out some of these properties, but the results are not well constrained. It didn't work that well. You need dedicated instrumentation for this sort of stuff. Often, as you would expect, our current expertise in, well, how the ground below us is based on our Earth experience, where we've got clays, pore water, groundwater, Earth gravity instead of 1/6 lunar gravity, and so on. And all of these differences are absolutely confounding in trying to solve these problems. So we can't rely on our comfortable assumptions that we've developed through years of civil, mechanical, geological engineering here on Earth. And the importance of addressing those knowledge gaps is being realized, like I said, and demand for the knowledge is increasing. Additionally, one thing that's challenging is that these sorts of properties and studies are often viewed as relatively low priority, even though they are fundamental for every aspect of space exploration. Why? I personally don't get it, but I'm biased. So anyway, the motivation for a lot of my work is sustainable extraterrestrial human and robotic permanence, safe and efficient interactions with planetary surfaces, whether that's landing, roving, infrastructure development, or utilization of local resources. I keep talking about this regolith because, well, it's really the only thing on the moon or Mars right now. It'll be the primary feedstock for our ISRU processes and infrastructure development projects. The properties of the regolith vary from site to site, just like here on Earth. No two places of the ground are the same. But couple this with the extreme environment of the moon, the reduced gravity, the lack of atmosphere, the radiation, electromagnetic fields, huge hundreds of degrees temperature swings between the lunar day and night, and limited energy resources. And this gets really hard. And I'm fortunate enough to be actually looking into some of this stuff. I think it's just so cool. So that's a very long-winded answer to my first question, and we'll loop back to summarize that all at the end. But now, one of the next things we look at is that naturally follows from this is how can we characterize the in situ physical properties of superficial planetary regolith? Well, like I keep saying, we need to understand the site and be able to prepare it for whatever we're doing, whether that's developing a roadway or just analyzing it to see, hey, is it safe for my rover to drive here to go take some science measurements? On Earth, when we want to do construction or exploration, we usually people go out and use specific and scientific instruments to measure the properties of the site and to come up with a specific plan of, hey, we need to compact the ground this much to be able to put this size of building on it and that kind of thing. We need the same kind of requirements for planetary bodies, but like I've hinted at, we don't actually know what those requirements are yet. There are groups doing great work helping define these requirements for, okay, if you have this size of a building, you need the ground needs to have these properties and that kind of stuff. But nothing officially published, and of course, nothing actually fully tested yet. The publications are coming out of really great groups like ASCE, the American Society of Civil Engineers. Our aerospace division is doing some really cool stuff with this. So like I said, the work is ongoing, but just need to actually go kind of test it on the moon kind of thing. So like I've said, we need to characterize in situ physical properties, and that brings its own whole host of challenges. Where we can, I don't want to bash our terrestrial Earth-based experience. Where we can, we should borrow from what we already know while carefully analyzing the assumptions we make. Where we can, here on Earth, we've developed simple standard tools that we use for exploration and site characterization, and for the purposes of what we can in space exploration, we should borrow from that too. The goal is generally to minimize mass and design requirements to make things simple and as cheap as possible, while still getting the right job done. One project I'm working on this front is the Cold Arm project with NASA Kennedy Space Center Swamp Works, and it's led out of the NASA Caltech Jet Propulsion Laboratory, JPL. I'm a collaborating scientist on this and one of the lead science investigators on this project. It's the general goal of the project is to develop a robotic arm that can operate in the cold of lunar night without heaters or to keep arm joints warm and lubricated. I won't dive into the specific robotic arm technology here, But what we were interested in testing this robotic arm concept with was actually taking geotechnical measurements on the moon. But to do that, we need to actually test and to be able to inform our results that we will eventually get on the moon, we want to test here using these high fidelity simulants here on Earth. To do that, the JPL team developed this specialized geotechnical scoop for cold arm. And by the way, the arm on the right is just a generic robotic arm at Kennedy Space Center. It's not cold arm itself. But so so JPL sent the team and I at KSC a scoop. We put it on the robotic arm with a force and torque sensor, and we did some experiments that I'll be outlining here, but to, get a sense for what forces and displacements are involved with actually operating this on the moon. The experiments we ran include angle of repose, and again, I'll be describing all these in a minute. Angle of repose, pressure sinkage testing, shear testing, some excavation or scooping tests, because it is a scoop, as well as a few other things. The angle of repose, which I'll show in a minute, but it gives a good first order look at the strength of the material you're working with. Pressure sinkage testing provides information on bearing capacity and trafficability. The shearing experiments are really important for things like trafficability, bearing capacity. Shear strength plays into everything, and it's kind of the hot thing to be able to characterize if you're doing in situ geotechnical tests. So we were looking at the cold arm scoop and robotic arm's ability to actually characterize that property. Excavation is a really good set of tests to run because it combines horizontal motions with vertical forces on the regolith, and we don't really understand how the regolith fully behaves under these situations, so we wanted to test some of that out too. For the angle of repose tests, like I said, it gives you a really good insight into the high-level physical properties of your regolith. It's not an extremely quantitative analysis, but it's useful for initial exploration, characterization, estimating rock distribution, and that kind of thing, because you want to know how many rocks are around you for exploration and science purposes. So to do this, we actually took multiple scoops using the cold arm scoop on the robotic arm. We programmed the arm to take a bunch of scoops and dump them into a pile. Really simple test. And the angle of repose is the angle of the slope of the pile. So we did that. We made piles of a given size and then just measured the angle. For if we were to see a really, really steep pile, that would tell us that the regolith is really cohesive. It sticks together well, and that kind of informs, well, how it may change how we want to dig in the future, or change a rover wheel design to explore that area, that kind of thing. Again, high level, just really general, nothing quantitative, but a good first look at, hey, what are we dealing with here? Is there anything crazy going on that we really need to consider? Another of the experiments that we were doing with the cold arm scoop is pressure sinkage, which is quite literally push the scoop, the bottom and back of that scoop into the ground and measure how much force it takes to push to a given depth. It's really, you can actually do a lot of really cool math on this. It's such a simple test, yet there's so much you can squeeze out of it. But you can analyze these data to predict rover wheel performance, calculate safety factors for infrastructure development, like if it's a roadway or a building. You can know how much that things are going to sink when you put something on there, which is really important, because if your rover wheel sinks too much, for example, it may slip, and if you get a slipped wheel, it's not moving, and then when you get one slipped wheel, the other wheels have to compensate for that to try to move the rover forward, and they start slipping, and eventually you're stuck. So it's really good to actually have an understanding of how the pressure sinkage relationships of the area you're in, for astronaut and robotic equipment safety, among other things. This test provides information on the relative compaction. For example, if you push on the regolith and it's on the moon and it sinks a bunch, well, you got to watch out for your rover there. You're going to sink a bunch and possibly slip a wheel or just get stuck. Whereas if it's pretty firm, you push with a given amount of force and you're not going to sink in very much. That's probably safe to drive on or walk on, that kind of thing. And there, like I said, there's a bunch of different ways you can actually analyze these data. And I give some examples of models down here on the bottom that relate pressure P to sinkage Z through various other parameters. And I won't dive into it here, but you can see there's different levels of complexity here. And these are pretty simple equations actually for this. And modern studies have gotten a lot more complicated with it. And it's super cool. Yeah, anyway. The next cold arm experiment we did was the shearing experiments, where we tried to test the shear strength to inform on traction, load-bearing capabilities, and material handling. The cold arm scoop has this little grouser on the back of it that we can use to compress and shear the regolith and get a lot of useful information out of that as well. And excavation, again, it is a scoop. It can tell you a lot about the properties of the regolith, rock conditions, and stuff like that. And hey, we need to, like I said, we're going to be excavating regolith for use in construction, resource utilization. So we actually wanted to get a handle of, well, how much force does it take to excavate this kind of stuff with a given scoop size? Obviously, this scoop is very small, and we're going to be using bigger things for actual excavation, but it's never bad to have exemplary data that you can study to base things on in a proof, especially from a proof of concept mission like cold arm is. So that was kind of looking at the surface of the moon. How can we characterize that very surface? We are also worried about the subsurface. And how can we look? My question is, how can we characterize what the subsurface behaves like instead of just those top few centimeters or so? To do this, I'm actually working with a team that's, again, led out of NASA JPL, but in collaboration with the Southwest Research Institute, SWRI, the Johns Hopkins University's Applied Physics Lab, or APL, NASA Ames Research Center, Honeybee Robotics, and, well, me at UCF. This is a regolith probe called SPARTA, the Soil Properties Assessment, Resistance, and Thermal Analysis toolkit. SPARTA enables us to take 4 parallel measurements relevant to both science and engineering tech development for the moon. It's kind of like a Swiss Army knife regolith characterization tool is how we've been describing it. So low mass, low power for shallow subsurface characterization. It's got a cone penetration tester, a vane shear tester, a dielectric spectroscopy probe, and a thermal conductivity probe. I'll explain all of these each in turn. In short, the cone penetration tester is quite literally measuring the force it takes to push a cone of given geometry, like the one we see here on SPARTA, into the ground. So literally measuring force versus depth. And this can tell us a lot about the stratigraphy of the moon or wherever we're testing. If there's really weak or strong subsurface layers, that's good to know for infrastructure development, mobility, and it's really informative on the geologic history as well. Directly from this, the cone penetration test is founded on Earth, used commonly in civil and environmental engineering studies. As such, it's really well characterized and can tell you a lot about trafficability, bearing capacity, drilling requirements, what have you. And these have been actually sent to the moon in the 60s and 70s on the Apollo and USSR Lunokhod missions. So high heritage, very simple, conceptually easy test. And based on this, you can actually kind of get an understanding of the relative level of compaction of the ground beneath your feet, which again, good for mobility and science. For the vane shear tester, this one's pretty conceptually straightforward as well. You see these little veins sticking off of the body of SPARTA. Well, that's because, well, when we fully stick SPARTA into the ground or the simulant that we're testing, then we rotate it and measure the force it takes to rotate. And that tells you a lot about the shear strength. So mechanically, SPARTA tells you about both the compressive or kind of vertically loading properties of these regoliths or simulants, and the vane shear tester, the VST, tells you about it in shear, in rotation along the horizontal direction. Really informative for both science and engineering. We SPARTA kind of does it all. I love this thing. So again, you expect to see a higher resistance to that rotation, to that rotational shear of the regolith with depth. And this is the plot on the bottom is an exemplary test case of us testing SPARTA at different depths and showing that, hey, as you go deeper, the force increases quite a lot. Again, useful knowledge, and this testing has great roots here on Earth as well. Civil and environmental engineers do this kind of stuff a lot, and we're just kind of borrowing from them. SPARTA, one of the relatively new things that it has that other people aren't doing and haven't been flown before are dielectric spectroscopy probes, or DSPs. Effectively turns SPARTA into a circuit to test different, to help detect different water ice, which is thought to be found on the moon in permanently shadowed regions, that we can get to help make rocket fuel in situ or for human use or whatever we're doing on the moon. You need water for lots of things. And if it's there, that just means we have to launch less. And this tool, this part of SPARTA, helps us find it. So it helps us find the water, the form of that water. It's all going to be ice, but is it like discrete grains of ice? Is it just thin coatings on mineral grains? All open questions, and SPARTA is going to help us answer that through its DSPs. The data that you see on the right here, I won't really dive into it, but effectively what I'm trying to show is that in a suborbital flight test we did on the Blue Origin New Shepard 29 flight back in May or so of 2025, we see differences in the readings versus gravity and how the water in our samples was flowing as a function of gravity. So the DSP is able to actually detect these things down to really low, really low concentrations, which is perfect because there's not going to be a lot of ice anywhere on the moon. But what's there, we need to actually be able to get out and measure. Last component of SPARTA is the thermal conductivity probe. The TCP tests thermal properties, whether that's temperature or how much heat the regolith is able to store, how well it transfers heat. Things like thermal conductivity are really important. And what we do is we stick SPARTA into the ground, we heat that thermal probe up. Like you see in the plot here, you see temperature rising, delta T, change in temperature. You see the temperature rising as we have the heater on. We turn the heater off and you watch the temperature fall again because the heater's off. There's no more heat being put into the system. And based on this temperature rise and fall of whatever SPARTA, whatever regolith or simulant SPARTA is in, we can do a lot of fancy math. And here's some of the equations to actually estimate relevant properties like K and D, which are thermal conductivity and diffusivity, key things to know for various purposes. We know the change in temperature, but we've got to solve for these, and there's a bunch of really cool theory that we do to back those properties out. Whoops. So that's a crash course on SPARTA. We are actually seeking manifestation for that on landers, rovers, astronaut tools, so hopefully one day we get SPARTA to the moon, and hopefully soon. And the last question that I'll pose here today is, how do the physical properties of planetary regolith affect rover trafficability? In other words, how well a rover can drive over the ground, and vice versa. How does a rover affect the ground? How does the ground affect the rover? It's obviously a coupled system. They each affect each other, but we don't really know how. So a bit of background is that mobility on planetary surfaces is extremely challenging. You've got reduced gravity, which does not help traction for wheels. You don't have as much downforce actually holding you onto the ground. Um, the lack on the moon, the lack of atmosphere causes a lot of interesting physical phenomena like electric fields, plasma environment, hard to deal with for electronics and for people. And like I've kept saying, the less than friendly physical properties, the hard to work with regolith. So we need to actually test rover wheels, how we drive the rover, like what speed, how hard we turn the wheel, and stuff like that. Speed, torque, wheel longevity, acceleration or deceleration profiles, performance and reduced gravity, and so on. We need ways to test that here on Earth. And we need to develop computational models to actually be able to predict these things in the lunar environment, because obviously here on Earth in a lab, we can't perfectly recreate the lunar environment and test all these things. So you need to be able to do some simulation, but base those simulations on your experiments. And here I'm going to describe a couple of the way that our lab group goes at that. The first one is called RIDER, the Regolith Interactions for the Development of Extraterrestrial Rovers Wheel Testing Bin. This project was done in collaboration between UCF and the University of Notre Dame under the Center for Lunar and Asteroid Surface Science, part of NASA's Solar System Exploration Research Virtual Institute, or SERVI. Now that the alphabet soup's out of the way. RIDER is a full-scale rover wheel and planetary terramechanics testbed. Terramechanics just being the study of how the wheels interact with the ground. In this bin, we've got gravity offloading capabilities, or custom load application. We can simulate a wheel in reduced gravity with this. Custom wheel mount system, because no two wheels have the same bolt hole mounting pattern on rovers. Dust mitigation, because like I keep saying, this stuff is dusty, and the high fidelity simulants we used are as dusty as the actual regolith. So we need to contain that for human and lab cleanliness. We have illumination and video recording capabilities, and naturally, this is a science test bed, so it records all sorts of data, which I'll go over. For scale, this bin is about 4 meters long by about 1 meter wide and half a meter deep. It is housed at the UCF class Exolith lab, where we have on hand bulk simulant production capabilities. So we do generally have this filled with lunar regolith simulant, but if someone wanted to test a Martian regolith, a wheel for a Mars rover, we do make Mars simulants as well, so we could just swap that out to test in the appropriate material. Some of the subsystems on RIDER, like I mentioned, are a gravity offload or load application system, where once we have the wheel mounted, our system automatically puts the wheel on the ground and makes sure that as it rolls, the proper force to simulate the wheel is applied to the wheel. For example, if we wanted to simulate a 100-kilogram rover on the moon, there's 1/6 gravity, so you divide that mass by 1/6, so 100 divided by 6, and then if there's 4 wheels, the load on the single wheel is that 100 divided by 6, whatever that is, offhand, I don't know, divided by 4. And that's what we put in, and that simulates the wheel in reduced gravity, or we can do it in full gravity, whatever you want, up to 200 kilograms, which is pretty good for a single wheel load. That's a big rover. So to do this, we have our motor box with a custom wheel mount setup. I think this is a wheel hub from some like Mitsubishi car or something, but turns out that terrestrial like car wheel hubs are really well sealed against dust in the environment. I mean, they have to be. So we actually just integrated a small one of these into our system. It's got a standardized bolt pattern that we can 3D print or machine adapters to go from whatever wheel we're testing to this wheel hub, so that we can interface with really pretty much any wheel that comes to us to be tested from NASA or other commercial or government organizations. We do have a variety of different motors that we use in this to explore different ranges of speed and torque and how that how that affects how the wheel interacts with the ground, and so on. We also worked really hard to develop a system to actually compact the regolith to match what the astronauts saw on the moon. They did a bunch of testing, specifically like a cone penetrometer during Apollo 16 in the Highlands region, where they actually measured some of the properties of the regolith, like how dense it is down at depth. And we were actually able to recreate those data here, giving a realistic representation of, hey, this is what the actual ground is like on the moon. Let's drive a wheel across it and see what it does. Really cool, really cutting edge testing capability. Not a lot of other people are doing this that I've seen. So I'm really proud of it. We do have environmental controls on this as well, such as a dehumidifier, which we've done testing and noticed that in Florida the ambient humidity is really high, and that actually affects the properties of the simulant, how wheels drive across it, how excavator blades interact with it, and so on. So we want to try to minimize the variation in moisture and minimize moisture in general. So we do have these environmental control systems where that are involved with our dust mitigation system. We have an airlock where we do all of our simulant testing, so none gets out into the other lab or to the rest of the lab. We have air filters to keep the air in rider and in the working areas clean and safe for us working there. We also, like I said, we have a lighting system and video, lots of video cameras that can be mounted pretty much anywhere within rider to record wheel interaction experiments from pretty much any angle that we want. It's also the control and data logging system is really easy to use. It's a box with a few switches that interface with a laptop to stream data, and also to SD cards and text files for later analysis. Now, I'll quit talking for a minute. I want to show you guys some of the testing that we've actually done in Rider, because videos are always the cool part, right? During the initial test campaign of Rider, we were given 3 different wheels to test by some very generous organizations. This first one is the Astrobotic Polaris prototype wheel. So the company Astrobotic is developing their Polaris rover, and they had this old wheel sitting around, old design. They're not using it. It's kind of beat up from some of their testing, but we were asking around, hey, does anyone have any rover wheels we can test in this thing? And Astrobotic said, yeah, sure, here, we'll send you one. So we ended up testing this wheel, as well as our colleagues and collaborators at NASA Glenn Research Center, who were willing to send us a couple wheels for this project, including this kind of a prototype of a wheel for the upcoming Viper mission, which is going to the lunar South Pole to look for water ice and do some other fundamental science investigations. The final wheels for Viper look quite a bit like this. This is a precursor to Viper's wheel. It's the Resource Prospector. That project kind of morphed into Viper over the years, and this is one of the wheels from that. And again, really similar to what's going to be on the moon soon here. Us just driving it back and forth. And like I said, we do drive these wheels at different speeds. So this is pretty much the maximum operational speed that they plan to run Viper on the moon. So we're actually seeing, hey, this might actually be what the ground looks like after this wheel drives across it. Similarly, a completely different design of a wheel, but this is a replica wheel from the Apollo mission lunar roving vehicle, the rover that the astronauts actually drove around on the moon. The kind folks at Glenn actually loaned us a replica of these wheels to test in this rig too, alongside the other 2, and compare results. This one's a very interesting wheel. It was my favorite one for historical significance and just because it looks really, really cool. It's effectively an airless tire. The other 2 wheels were perfectly rigid, and seeing how this wheel that, like, you can see it squishing out at the bottom. I'll play it again. You can see it squishing out at the bottom like a tire would if you put a bunch of load on it. That's to help give the wheel more traction on the ground. More area on the ground means more traction. And yeah, you can see that the tracks look completely different. There's no like digging into the ground, into the simulant with this one. Whereas the other two, because they had grousers along them, kind of chewed it up a bit. There's a quick visual comparison, LRV, Viper. And there's advantages and disadvantages to both. I won't dive specifically into that right now. But so we visually see that, hey, yeah, driving on this stuff really impacts it. It can dig it up with the grousers, or if a wheel slips, you're just kind of stuck, kind of thing. But we wanted to add some science to these observations. And those 3 wheels were tested in the Gator test campaign, we call it. It was the geotechnical assessment of regolith on trafficability. In this study, we tested these 3 wheels. We ran them back and forth 900 times each. We stopped every 100 passes to take samples of the regolith for particle size analysis to see, hey, do the particle sizes change as we drive over them? Are things flowing around, or are grains getting crushed under the wheel after this many passes? That kind of thing impacts the properties of the regolith, like the strength. Are you making it, by driving on it more, are you making it even harder to drive on? That kind of test. Open questions in the field that we're working on answering. So we stopped every 100 passes to assess the simulant. Is it getting denser under the wheel? Or is that particle size distribution changing? And so on. Like I said, we had this compacted, the simulant and rider compacted to match the Apollo 16 stratigraphy, and actually use the same size cone penetrometer that they used for direct comparison. And I won't dive exactly into this, but what I'll show you is that in general, on the left-hand plot, you would expect the dots to be kind of around or on or between these lower 2 dashed red lines. But as we drove on them, as we drove across the ground, it got more and more compacted, making it harder and harder to push that cone penetration into when we tried to after 100 wheel passes. In other words, we're compacted, at least in the lower parts of the test bed, we're compacting as we go over it. But in the top parts, the wheels with grousers are fluffing it up, shearing it, making it harder to drive on. Interesting operational consideration. And as you can see, the penetration depth versus stress, which think of it as force in this case, as we got more wheel passes, it got harder and harder to push into the same depth. So again, the ground is changing under us, and that's really important to know if we're sending, rovers that cost millions and billions of dollars to drive back and forth, delivering people, cargo, whatever, what have you, on the moon. So really important information. We're still working on data analysis for this. We're working on getting it published, so stay tuned. So that's the experimental side of the wheel traffic stuff, and I promise I'm almost done here. On the computational side, one project we're working on is called SPIDER, the simulator for planetary interactions with dust and regolith. This is a discrete element modeling simulation for rover wheel interactions with regolith in planetary environments. We can take a prototype wheel geometry in a standard format, something like a CAD design, for example. We can put it into this simulation where we specify the gravity, the ambient electric fields, and vacuum or not. And we run the wheel through the simulant, and we get information on the wheel's efficiency and how much dust you're throwing around. You don't want to be kicking up a ton of dust, because if that dust gets on sensitive electrical systems or around human habitats, that's not great. You don't want to be lofting a ton of dust. So this is a way for us to track where does that dust go and what wheel designs are better for minimizing dust in the lunar environment. To calibrate these models, however, we need data. And this is a video. Let's see if, oh, I don't think it's gonna play. Cannot play media. Oh, bummer. Well, I'll move ahead, because I have a picture of it here. But what we end up doing is we got actual lunar regolith samples, which shout out to the Thermal Infrared Emission Spectroscopy Lunar Sample Characterization Consortium, a group of scientists who actually loaned us these samples to do these experiments. So what we do is we effectively raise a cylinder that we had filled with the regolith samples and simulant samples, and then model the same thing in the simulation, and then try to, turn the knobs on the model to actually see what best fits the actual data we got. Once we have that, we can actually, and we know our best fit parameters, we plug those into our wheel simulation, and off we go, actually studying dust transport caused by rovers and electric fields and so on. We try to approach this from both the experimental and computational side, because to properly study terra mechanics and develop mobility systems, experiments and predictive models are not enough on their own. They need to be coupled. You can't have an experiment here on Earth and assume that it's going to be representative of what actually is going to happen on the moon. But similarly, you can't just have a computational simulation without it being validated by real world results. So that's our design and approach for this. I will say that the Rider and Spider teams we work with people regularly, academic, government, and commercial researchers, to actually tackle problems in planetary mobility. So if anyone's interested in more in this, even just passingly, if you have a passion for rovers, let me know. I can send you more information. And if anyone wants to work on stuff like this together, please let us know. So to wrap up, I see that I'm very likely over time here. So to wrap up, what testing materials do we need for scientific research and development of hardware for space exploration and settlement? That very first question I posed. Well, I pose that we need high fidelity mineralogy-based simulants that are available in bulk quantities. Our group here at UCF has made this possible for the first time through the Exolith Lab and corporate spinoff Space Resource Technologies, who actually handle the day-to-day of selling the simulants. These simulants need to be based on mineralogy and particle size distribution, since these are the two fundamental drivers of pretty much every aspect of the simulant's behavior, physically and chemistry. The next question I posed was, well, how can we characterize the in situ physical properties of subsurface planetary regolith? So we need dedicated surface-based instruments, whether we're trying to characterize that very top layer of regolith or deeper down in the surface. We need dedicated, well understood instruments that can be deployed by astronauts, rovers, mounted on landers, and so on, to enable mapping of the physical properties of the regolith and help us find sites for infrastructure development, safe rover traverses, places to look where we can access water ice, and that kind of stuff. Then the third question I posed that we just quit talking about is, how do the physical properties of planetary regolith affect rover trafficability and vice versa? Well, the physical properties of the regolith or simulant directly impact wheel traction. If you're in a really loose or fluffy regolith, your wheel's going to slip, your rover's going to get stuck. If you're on a very hard and compacted surface, it's easier to drive on. And as you drive more and more over these surfaces, they do change. And how they change depends on your wheel design, which is, I mean, it makes perfect sense. It's intuitively obvious, but we need to do the work to actually quantify this, to be able to give guidance to rover designers, to NASA and others, for actually how do we best do this, keep our people and equipment safe. And that's actually all I had. I realize there's no one on the other end of this right now, but Sumana, if you have any questions, anything you'd like to ask, please, I'll quit sharing.
First of all, Jared, I think this is fascinating to say the least. I think the moon, and why I love people who try to do lunar research, is that the moon is kind of an engineer's paradise. I mean, the regolith is so different from what we see on the Earth soil. The radiation environment is crazy there. The atmosphere as we know it is not there. And that makes even the little engineering achievements that we have on Earth seem like such a huge hurdle. And what you explained is, if I can use the word, it's mind blowing. And it's one of my favorite fields to study in space. Thank you so, so much. And since it's just the both of us, I'm literally trying to absorb what you said and think that how much progress you make starting from the initial research to actually testing. So much happens before we go to the moon based on what people have told us after the Apollo and the following mission. So thank you so much for this.
Of course. No, I realize I probably rambled on and on, but this is absolutely my passion too. And yes, this I mean, there's an old saying in the field, space is hard. Space is very hard. And failure is not an option, it is a must. You must fail. We will fail. We will try again. We get back up. That's what we keep doing. And like you said so well, even the tiniest achievement in lunar science and engineering is such a monumental thing. I mean, it took how many people, how many hours, how much money to just get to the moon the first time, and we're trying to go back and do it completely differently now. Of course we're still learning, and I'm so excited that this is just the beginning. Things are going to get really cool here in the next decade or so.
I'm sure it's going to happen. And I wish you and your teams all the best, that you keep taking the research forward, because the more you do this, the more it becomes easier to answer, okay, this is why we need to go to the moon. This is why we need to do space research.
Yes.
Thank you, Jared. And to everyone watching, please subscribe to this channel on YouTube and follow this podcast on Spotify, because there are many, many such cool professionals in space who we are going to see come to the podcast and tell us what they're working on. So thanks a lot, and I wish you the best.
Thank you, everyone. Thank you, Sumana. See everyone later.